Okay, this video is just sort of to wrap up this section on nuclear chemistry and just some practice questions to practice some of the calculations that we've gone through mainly. So the first one is the half-life of plutonium-239 is 24,110 years. How long must pass until the amount of plutonium-239 decays from 1 mole to 0.202 moles? So that's using our NT equals the amount of stuff at time t is equal to the amount of stuff initially times e to the negative decay constant times t. So we know that the amount of stuff we want at time t is going to be 0.02 moles. The amount of stuff to start with was 1 mole, and our decay constant is the natural logarithm of 2 divided by the half-life. The half-life is 24,110 years, so that's the natural logarithm of 2 divided by that is 2.8749 times 10 to the minus 5. The ratio between the amount of stuff at time t and the amount of stuff that we start with is 0.02 because we started with 1 mole, and that's equal to e to the negative 2.8749 times 10 to the minus 5 times t. The log of that is equal to negative 2.8749 times 10 to the minus 5 times t, and t is equal to the log divided by the decay constant, which is equal to, so we can work out that t would be 136,073.4 years until that 1 mole decayed down to 0.02 moles of that plutonium-239. So that's an example of one of the calculations we learned how to do. Something else that we learned how to do was to balance these nuclear reaction equations. So here we have thorium-232, and it's decaying down without the decay, so we're going to lose 4 from the, so you want to make all the things at the top add up. So 232 minus 4 is going to be 228, and 90 minus 2 is going to be 88. And what element has atomic number 88? That's right, it is radon. Sorry, radium. What am I saying? So radium is what it decays down to, and that would probably decay on further to something else. And in this case, so we're going from 63 nickel 63 to copper 63. We're going up. So what's going to be released here to go to gain a proton? Well, one of our neutrons is being turned into a proton, so thinking of conservation of charge, you need to spit out something negative. So -1, the mass doesn't change, but that changes, and you're spitting out a beta particle or an electron. So those are the two types of balancing nuclear equations that you might have to do, being given what particle's been injected and work out what molecule's been formed, or being given what molecule it's decayed down to, what element it's decayed to, and work out the type of decay. And then the last question is also pretty straightforward. So tritium, hydrogen 3 has a half-life of 12.26 years. What is the molar activity of tritium? So if you had 1 mole of tritium sitting on a bench, how many times would it decay per second? So how many decays would happen per second? So the activity is equal to negative dn dt is the decay constant times the amount of stuff that you have. You have 1 mole, that's 6.022 times 10 to the 23 particles, and the decay constant is equal to the natural logarithm of 2 on the half-life, and you need the half-life in seconds if you want the molar activity in Becquerels, which is decays per second per mole. So it's natural logarithm of 2 on 12.26 times 365 days in a year, approximately, times 24 years times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute. So that's natural logarithm of 2 on 386,631,360, and that's 1.793 times 10 to the minus 9. That's your decay constant. Then, as 1 mole of stuff is 6.022 times 10 to the 23 particles, that means your activity is equal to the decay constant times that number of particles, which is 1.07758 times 10 to the 15 decays per second. So that's 1.078 times 10 to the 15 becquerels per mole of tritium. So that is your molar activity for tritium. So just to recap, that just recaps working out amounts of stuff after decay, activities for things that are decaying, and also balancing equations, and just to get back into remembering different types of decay, like beta decay and alpha decay and whatnot. So I hope you enjoyed the nuclear chemistry part, and onwards and upwards to some quantum chemistry and talking about bonding and whatnot.